fourth and final video on derivatives and logarithms. And of course we're talking about both derivatives of logs and logarithmic differentiation and the fun things that we can actually figure out from those processes. Let's go ahead and dive right in. The last problem that we did in video number 3 was one where, we could have, and I'll go ahead and pop it back up, we could have done the derivative here just by grinding out, chain rule inside of quotient rule and stuff like that. But by imposing a logarithm from without, we're actually able to use the properties of logarithms to pull that huge product slash quotient apart into its constituent parts such that I could differentiate each of them independently. So it's always a little bit easier to pull something into its parts and deal with it piece by piece than it is to deal with the whole thing all at once. This was probably a good move, especially if what you're going to be doing with the derivative next doesn't require it being in a single rational expression. Now, if you need the derivative to be in a single rational expression, and of course you'll understand what that means a little bit fuller as we get into the next chapter, you might actually want to do it, starting here and doing it by the quotient rule. But if you're just trying to maybe, evaluate it, or if you're just asked for the derivative, quadrivative, just do it by logarithmic. Much easier. Okay. Let's do another example, kind of like that. How about y is equal to x cubed plus 1, x to the 4th plus 2, and x to the 5th plus 3. Now this is certainly a little bit more on the border in terms of whether you would want to do it, because there are two things you could actually do. This is actually, it's doable to go ahead and multiply this all out into a polynomial. Now, not fun, but it would only take a couple of steps, and then at that point, since this is a binomial to the first power, a binomial to the first power, and a binomial to the second power, I could then take these and put it term by term and differentiate it term by term. It's very, very doable. Tedious and, unenjoyable, sure, but doable, right? But it is probably a little bit easier to go ahead and apply the logarithm from without and pull it apart into its pieces like so, and then differentiating each of these independently winds up being a rather straightforward affair. 4x cubed over x to the 4th plus 2, and then make sure that you don't forget the 2 right here. So that winds up being 2 times 5x to the 4th over x to the 5th plus 3. And then the last thing you have to do is you have to multiply both sides by y. And by y I mean this whole expression, right? Don't stick a y over here when there's an x expression in terms of, there's an x expression that y is in terms of, such that your derivative can be stated in terms of a single variable. X to the 5th plus 3 squared, and then just make sure that you're being careful with all of your parentheses and your brackets and all that sort of fun stuff. We don't want to get it wrong because we've made a careless mistake in terms of our notation. That would of course be a crying shame. And that right there winds up being our derivative. Now, a little bit more difficult than that are the ones where they are required. But before we get to the ones where they're required, I want to sort of re-emphasize or restate how we actually are using logarithmic differentiation sort of behind the scenes when I get 5x to the x squared minus 2x, okay? Because that's an exponential, okay? And, we've talked about the fact that it does not abide by this rule, right? This rule is for variables raised to constants. This is a constant raised to a variable expression. So the relationship is reversed, right? And so, what we have here, and why we don't use n as the base, we use a as a base, I guess it's just an arbitrary choice. And actually this is not x, this is u, right? It's an expression in terms of x. So we get a to the u times natural log a times u prime. So f prime of x here is just, you just rewrite the exponential, then you take the logarithm of its base, and then you take the derivative of that exponent expression, okay? And that winds up being a to the u, natural log a, u prime. But of course, you could have done it the long way. Let's say you're like, oh, I'm never any good at that. I'm never any good at memorizing formulas. And you know me and formulas. I can't stand formulas. The only time I use formulas is when I've accidentally memorized them. Otherwise, I'd rather just go through the process. It winds up just being a little bit more natural in terms of, my perspective, but whatever. Because when I take the natural log of both sides, it's going to be natural log 5 to that. And of course, that being the exponent in terms of rules of, or properties of logarithms, you can bring it down in front. And then it becomes y prime over y. And this is just a coefficient, right? So the coefficient just comes along for the ride, and you get 2x minus 2. Well, here's your natural log 5, 2x minus 2. And of course, the 5 to the u just comes along when I have to multiply both sides by y in order to isolate the y prime. 5x squared minus 2x times natural log 5, 2x minus 2. Voila, there you go. Now, of course, this winds up being relatively straightforward. The only time that it can get a little bit complicated is if your teacher throws you a curveball. And by curveball, I mean just something that, you don't see very often, so it kind of makes you pause and freak out. Now, why is that any more difficult than the last one? Well, the answer is it's not. It's actually easier. The reason why it looks harder is that despite the fact that you have a numerical base, the numerical base doesn't look numerical. It looks like a variable because pi doesn't look like an Arabic numeral. It doesn't look like 7 or whatever, okay? But it needs to be treated exactly the same way, okay? So that's a to the u times natural log a times u prime. That is your derivative right there. Now, there's one thing that we haven't done, and we haven't done a whole lot of logarithm or differentiation of logs when the log is of a different base. Okay. Now remember that this winds up being the reason why the rule is what it is the fact that you can always change the base of a logarithmic expression. And so the reason why the rule is what it is, meaning that it's y prime is equal to natural log a times u and then u prime on top. The reason why it's like this is because behind the scenes, lurking behind the scenes, is this move right here. Okay, because the moment that you make this move, you recognize since natural log 5 is a constant, you basically are doing differentiation of a natural log function just with this pesky little coefficient coming along for the ride, which is, of course, right here, right? Okay, so let's go ahead and do a few problems where the whole aspect of logarithmic differentiation is not, it's not a good idea. It winds up being absolutely necessary. Let's look at, how about y is equal to x e to the x, okay? Now remember, I said that you probably could go ahead and at least memorize the x to the x. right? The x to the x winds up being pretty simple. It winds up being x to the x 1 plus natural log x once you're all said and once all is said and done. But here, this is x to the u, right? So x to the u, let's go ahead and just take the natural log of both sides. And the moment that I take the natural log, this is going to be natural log x to the e to the x, which then, of course, I just bring down in front, right? Now, when I differentiate both sides, it's going to be product rule, okay? And therefore, it's e to the x times the derivative of the second, the derivative of the first times the second, and this is y prime x to e to the x, and then I guess you could pull out an e to the x since it is common to both of those terms from the product rule, 1 over x plus natural log x. Now there was really no other way to do that. I'm going to try to remember to forward you a funny little article that I found on the Mathematics Association of America website about two wrongs make a right. If I get to forward that along with the links to the YouTube videos, please do shoot an email back to me and let me know that I've forgotten it, because I would like. Some of you may find it sort of humorous. It's kind of one of those things that when you're a teacher you kind of stumble upon. You kind of go, isn't that interesting? But that is basically what's going on here. Now, like I said, you can try to make a rule, right? You could say, okay, let's do y is x to the u, where u is, of course, as always, some expression in terms of x. And so we have natural log y is equal to u times natural log x, and you get y prime over y is equal to u times 1 over x plus u prime times natural log x, and so you get y prime is equal to x to the u over x plus u prime natural log x. Now that doesn't look altogether different from the rule earlier, right? But then you have to deal with u to the x and then u to the v and stuff like that. So it just winds up being, I think, an unnecessary expansion of the number of things that you're already asked to memorize. And of course the things from Algebra 2 and Pre-Cal that you're supposed to still have in your memory bank. By the way, related rates coming down the pike, 3.9 in your book. You're going to need to remember your geometric formulas. And so we'll talk about that once I get started on the related rate videos. But I wouldn't memorize that. I mean, it's only just a couple of steps. This is way too complicated, and the odds of you making a mistake in remembering this formula are much higher than the odds of you making a mistake here in terms of the actual method of logarithmic differentiation. Let's do one more, and then we'll call it quits in terms of derivatives and logs, since this is the fourth video and we need to kind of get moving on to the new section since she seems to have accelerated. Now here, and when I'm doing logarithmic differentiation, I don't particularly like doing it with f. I like doing it with y. So I would go ahead and change this function here. And, we can go ahead and do the natural log of y. 3 to the x times natural log of x. And so we do y prime over y first times the derivative of the second plus the derivative of the first times the second, okay? And then, of course, you get y prime is equal to x to the 3 to the x. We can factor out of 3 to the x, and it winds up being 1 over x times natural log 3, or plus natural log 3 natural log x, okay? Now, there is one thing which might actually wind up getting in the way. Let's say you have y is equal to 2x to the sine x, right? Now, you're used to seeing y is equal to x to the sine x or something like that, but what happens with the 2? Well, you just have to be very, very careful to do your properties of logarithms in order, right? Because it's not the 2x that's raised to the sine x, it's just the x. So the moment that we do this, we have to recognize that natural log 2 has to be split off into its own term before you bring down that sign, okay? I don't know how many times I've actually seen sine x times natural log of 2x. That is not true, okay? In order to be that, you got to remember that 2x to the sine x is not the same thing as that. If it were 2x being raised to the sine x, there would be parentheses right there, okay? So that would be how you need to approach this type of problem in contrast to this type of problem. This is much more straightforward, but as long as you stop and think and remember that the properties of logarithms have to be done in a particular order in order to ensure that you're actually arriving at an expression that is equivalent. Because from here, when you differentiate, natural log 2 differentiates into 0, okay? And the 2 winds up being sort of kept around. So let's actually sort of box this up and let's bring it down here. Y prime over y is equal to 0 plus sine x 1 over x plus cosine x natural log x. And you're like, well, what about the 2? It looks like the 2 disappears. Well, the 2 doesn't disappear because you have to multiply both sides by y again. And y has the 2 tied up inside of it. Okay, so sine x times 1 over x plus cosine x times natural log x, and that would be your derivative. That kind of, that brings us to the end of our talk about logarithms and derivatives. I hope that's helpful, guys. From here, we're going to be launching into 3 sections of the book, 3 in a row, that deal with the application of the derivatives. I'm not a big fan of 3.7 and 3.8, and at times I've actually skipped them and gone straight to related rates in 3.9. But basically what they're trying to do is they're saying, okay, now that you have all of these nice, neat little tools for differentiating, let's talk about a little bit about how the derivative is now applied to some particular circumstances. So we'll talk about that in the videos to come. So that's something to look forward to. Bye.